Today we're going to talk about the length of a curve described by a vector function. In talking about the length of a curve, it'll be important for us to briefly revisit and define what is meant by the velocity and acceleration of a curve. Once we have that understanding, we can then talk about the length of a vector function along the curve. And finally, we'll be able to discuss the arc length function and use it in order to find the arc length between 2 points on a curve. So you may be wondering, why is this important? More than just being a mathematical construct, vector functions have numerous real-world applications. Now remember, a vector function is a vector whose components are functions. So let's take a position vector, a vector whose components are the coordinates of position based off of the parameter t. We could use the analogy that t represents time. So the x-coordinate is the x position as a function of time. The y-component is the position along the y-axis as a function of time. And the z-coordinate is the position along the z-axis as a function of time. T could be any parameter, but time is a useful analogy. Well, let's say, so vector functions can be used to describe the trajectory of objects, for example. What if we wanted to launch a probe from Earth to the moon? And that probe might follow a particular trajectory that can be predicted. So let's say this is our probe at some point along its path in its journey from Earth to the moon. We may be interested in knowing where the probe is at various moments in time. So if we could parameterize the curve as a function of time, we can predict where the probe is going to be. So let's say after 2 days, we want to know how far the probe has traveled. Maybe after 2 days, the probe is right there. This would correspond to a certain length of the curve between its starting point and the point after 2 days. And then maybe we're interested in knowing how far it travels between 2 days and let's say 4 days. Between 2 and 4 days, that would be a certain segment of this curve given by a particular length. Now, this is just one arbitrary example of many different types of applications that we could use for the arc length function. So to have a better understanding, let's talk about the tangent vector and its relationship to the velocity of a curve. Remember, the tangent vector of a curve is equivalent to its velocity. Well, the velocity of a curve is the rate at which the position of a point on the curve changes with respect to the parameter t. In other words, velocity is the rate of change of position with respect to the parameter t. If we continue using the analogy of t being time, you can think of velocity as being the time rate of change of position. So if we are looking at our space probe to the moon example, and we look at the probe, let's say, at this point on the curve, defined by a position function at that point, I'll just call this point A. So the position function at point A will have a corresponding velocity vector. And this velocity vector is going to be tangent to the curve at that point. This velocity vector is equal to the derivative with respect to the parameter t evaluated at that point A. If we look at a different point on the curve, let's say a later point, we will call this just point B. The velocity vector at point B is, again, the derivative of the position function evaluated at the time t equals b. By knowing the rate at which this curve changes, and notice the velocity changes at various points because the direction changes, its magnitude changes, may change. By knowing the position vector and the velocity vector, we could describe how this curve changes in space and how fast it changes. Now, how fast the velocity vector changes brings us to the acceleration of a curve. The acceleration of a curve is the rate of change at which its velocity changes with respect to the parameter t. So that's just simply equal to the derivative of velocity with respect to time. And remember, velocity is the derivative of position with respect to our parameter t, or time, which means that the acceleration vector is just the second derivative with respect to our parameter t of position. Now, what does the acceleration vector correspond to? Well, again, it corresponds to the rate of change of velocity. So, for example, let's look at the launch of this space probe from Earth. Notice how curved that path is. It's more curved at the beginning of its voyage than it is for other points on the voyage. And if we are to look at the velocity vectors, this space probe might start off with a very small velocity, indicated by a small magnitude. As it picks up speed and adjusts its orientation, the velocity may increase. And so if you look at that, not only does the magnitude of velocity change, but in this case the direction changes dramatically. That change of velocity with respect to time is what the acceleration tells us. This brings us to the theorem for the length of a curve. Let C be a curve given by the vector position function r, with components of f of t being a parameterized function for the x component, another parameterized function g of t for the y component, and another parameterized function h of t for the z component on the interval from a to b, where the derivatives of f, g, and h are continuous. If C, the curve, is traversed exactly once as t increases from a to b, then its length is given by the definite integral from a to b of the square root of the sum of the squares of the derivatives of the components of the position vector, which is essentially the magnitude of the derivative of the position vector with respect to time. Well, let's talk about what that means. Instead of using f, g, and h, let's just use some more intuitive variable names. We'll say x, y, and z for the x, y, and z components. That makes a lot of sense to me. Let's look at the derivative of this. If we take the derivative of the position vector with respect to time, that is just the derivative of each of these components with respect to the parameter t, and I let slip. I called that parameter t time. Well, time is a useful analogy for the parameter t because when we evaluate the derivative of this position vector, oh, and look at that, position. When we evaluate the derivative vector with respect to the parameter t, that gives us the rate at which the position changes with respect to t, and the natural analogy for that is the rate at which our position changes with respect to time. So what this gives us is it gives us three components. It gives us a x component for the velocity of our derivative function. It gives us a y component for the velocity of our derivative function, and it gives us the z component for the velocity of our position function. So we could equivalently and analogously think of the time rate of change of this position vector function as being equal to the velocity of our curve. Now, the magnitude of the derivative of our position vector function is just the magnitude of the velocity. And remember, we call the magnitude of velocity speed. So when we describe the length of our vector function in a closed interval from a to b, we can think of this length as being the definite integral from a to b of the speed of our curve with respect to time. This probably sounds familiar to you, that this length is equal to the integral of a speed times time. Well, it's because in a class you've taken before, you've learned that distance is equal to speed times time. Now, these aren't exactly the exact same two quantities, but the idea is related, that the length of a curve between 2 points, if we traverse those 2 points exactly one and only one time, the length of the curve is described by the rate or the magnitude of the rate at which that curve changes with respect to time. So for me, I actually think of it as, when I'm trying to remember the formula, I kind of think of the formula as distance equals speed times time. Except we're dealing with vector functions that can change orientation in space, the rate at which this vector function can change. So instead of simply being distance equals speed times time, we have to say, okay, the length of this arc between these 2 points is a definite integral of our magnitude of velocity with respect to the parameter t.